Hi all, this is Priyadharshini working as an assistant professor in the Department of Artificial Intelligence and Data Science. Today we'll see the topic Dijkstra's algorithm as a case study. Thank you.
Everyone, today we are going to discuss about the topic Dijkstra's algorithm. Dijkstra's algorithm is a fundamental graph search algorithm used to find the shortest path from the starting node, that is the source node, to the other nodes in weighted graph. So the key concept of the Dijkstra's algorithm is its graph representation. It is representation in form of graph which contains nodes and edges and weights. The graph should be only weighted graph and the priority queue. Dijkstra's algorithm uses a priority queue algorithm and the distance table used to calculate the distance between nodes.
Needs for Dijkstra's algorithm. Dijkstra's algorithm is essential for finding the shortest path between nodes in various applications. In computer networks, it optimizes routing protocols, ensuring efficient data packet delivery. Geographic information systems like Google Maps use it to provide accurate directions considering traffic and distance. It is also crucial in robotics for pathfinding and navigation through environments with obstacles. Additionally, the algorithm aids in route optimization in the airline and logistics industries, helping to determine efficient flight paths and delivery routes. Overall, Dijkstra's algorithms enhances efficiency, reduce cost, and improve performance across numerous fields where optimal pathfinding is critical.
The ambiguity of Dijkstra's algorithm. Dijkstra's algorithm can work both on directed and undirected graphs. So it can work with any type of graphs as long as it meets its requirements of having non-negative edge weights and being connected. And in directed graph, each edge has the direction indicating the direction of traveling between the vertices connected by the edge. In this case, the Dijkstra algorithm follow the directions of the edges when searching for the shortest path. In an undirected graph, the edges have no direction. The algorithm can traverse both forward and backward along the edges when searching for the shortest path.
Implementation of Dijkstra's algorithm. There are several ways to implement Dijkstra's algorithm, thus the most common ones are priority heap-based implementation, array-based implementation. In the implementation, we are given a graph and the source vectors. In the graph, finding the shortest path from the source to all vertices in the graph. Initialize the distance values and priority queue. Insert the source node into priority queue with distance 0. Extract the node with minimum distance from the priority queue. Update the distances of its neighbors if the shortest path is found. Insert updated neighbors into priority queue.
Advantages: optimal solution, simple to implement, efficient, adaptable, application to real world problems, easy to understand, scalability, multi-source shortest path, handling negative weights, error handling, robustness, wide applicability.
Disadvantages: not suitable for large graphs, not suitable for graphs with negative edges, requires a lot of memory, not suitable for real-time applications, not suitable for dynamic graphs, not suitable for graphs with weighted edges, not suitable for graphs with multiple sources.
Dijkstra's algorithm will generate the shortest path from node 0 to all other nodes in the graph. Consider the below graph. Step 1. Start from node 0 and mark node as visited. As you can check in below image, visited node is marked red. Step 2. Check for adjacent nodes. Now we have two choices and choose node with minimum distance. In this step, node 1 is minimum distance adjacent node. So mark it as visited and add up to the distance. Distance node 0, node 1 is equal to 2. Step 3. Then move forward and check for adjacent node, which is node 3. So mark it as visited and add up the distance. Now the distance will be 7. Step 4. Again, we have two choices for adjacent nodes. Either we can choose node 4 with distance 10 or either we can choose node 5 with distance 15. So choose node with minimum distance. In this step, node 4 is minimum distance adjacent node. So mark it as visited and add up to the distance. Therefore, distance is 17. Step 5. Again, move forward and check for adjacent node, which is node 6. So mark it as visited and add up the distance. Now the distance will be 19. So the shortest distance from the source vertex is 19, which is optimal one. Thank you.